Alright, we are going to do a problem dealing with vectors and with a cross product. We are asked to demonstrate that vector w is orthogonal to vector v given the following information. That vector w is defined as the cross product of v and u, and that vector v is this in component form, and vector u is this in component form. So the first thing that we want to do is do the cross product of v and u so that we know what the vector w actually is as a single idea. So we're going to use the cross product. This is my cross product determinant written out here to the side to help me. And so I'm going to fill in the information. We want to create a matrix with I, j, and k in it. These are going to represent component pieces of a vector, the final vector, w. V, each of these components here are going to be substituted into here, and each of these components here are going to be substituted into here to create this vector. So we are going to have vector v cross vector u is going to be equal to the determinant I, j, k, and we want 2, 3, 2, 3, negative 1, 4, there. So I've just taken this set of numbers and put it in for my second row, this set of numbers put it in for my third row, and I have the I, j, k as my first row. And now we need the determinant of this. And you're probably going to have to do this manually unless you use a bigger program besides your graphing calculator. So you might need a computer to do this. If not, you're going to have to do this by hand. I'm going to break this down using this as my key row. So I want to create a set of determinants, 2 by 2 determinants that multiply by the ijk, and so if I'm using I here, this is manually doing this determinant. We're going to take out this column and this row and look at these 4 numbers left to fill in for this little determinant. If I'm looking at j, I'm taking out the column that contains j, the top row, and so I have 2, 2, 3, 4 that haven't been eliminated, and then k, take out the k column, top row, and I have 2, 3, 3, and negative 1 here. Alright, so hopefully this is a fairly standard high school version of a determinant. We're going to have a negative and a positive here. So now I want to find the 2 by 2 determinant here, which is I take this row, multiply it, this row, multiply it, and subtract those. So I'm going to look at 12 minus negative 2. So 3 times 4 is 12, 2 times negative 1 is negative 2. And whatever that difference is, we're going to have that multiplied by I. And then we're going to look at 2 times 4 is 8, minus 6j, negative 2, minus 9 is k. So now I have 12 plus 2 is 14, 8 minus 6 is 2, and then 9 ends up being plus 2. So I have 14i, negative 2j, negative 11k. So now this is going to be the components 14, negative 2, negative 11. And this is my components for vector w according to the definition I have up here, that w is defined as the cross between v and u. So now the first part of this problem says that I have to show that w is orthogonal to v. So how do we demonstrate that this is orthogonal now that we know what vector v actually looks like? Well, we want to do the dot product. We want to do vector w dot vector v to find out if these are orthogonal. If we do the dot product of these two vectors and it equals 0, then yes, they're orthogonal. If it equals anything besides 0, then they're not orthogonal. So how do we do this? So we're looking at 14, -2, -11, dot, the components for v is 2, 3, 2. So we're multiplying each of these terms in their places and then adding them to the other products. So 14 times 2 is 28 plus -2 times 3 is -6. -11 times 2 is -22. And so I'm going to leave the 28 here as I bring together my negative terms here. This is -28. So this is 0. So these are orthogonal. So we've answered this question. We have demonstrated that vector w is orthogonal to vector v. And we've done that using the dot product, but before we use the dot product, we had to use a cross product because w was defined as a cross product for this specific problem. Hopefully this has been helpful. Cheerful calculating.